Okay, so imagine a robot, imagine a goal, and then imagine there are obstacles on the way. Okay, we want the robot to go to the goal. So clearly there's one path is like this, another path like that. You could also go this way, just various paths to go to the goal. Okay. So you can find this problem can be set in various ways. You could say, what's the fastest way to go to the goal? It could be, what is the uh, path which minimizes some energy? So if you want to do with an optimization, you could do it. You could also try to head towards the goal. There's like a direction which you can head. And then when you hit the obstacle, move. So we'll basically talk about a bunch of methods to do it. Uh, the first one I'll talk about is kind of a very intuitive method. It's often known as well, it's the simplest way. It doesn't really have a name, but let's call it uh, go to goal and obstacle avoidance. Okay, it just combines two simple ideas, and then we should be able to put it all together and get a robot to move to a goal while avoiding obstacles. So the first thing is go to goal. So if you have a goal and if you have a robot, and then let's just assume it's a differential drive car. So the differential drive car has two inputs, a velocity input, and then I think we specified omega, right? Omega lets it turn, and then V lets it go straight. So it's a diff drive car. Okay, so what we do here is, if you want to go to a goal, right, you better be heading towards the goal. So what we have to essentially do is, if the location of the robot is x comma y, and usually it's some center point, we can draw a straight line like this. Okay, so let's call that the desired heading. So as long as the robot is heading to that direction, you're going to go to the goal, right? So what we'll do is we'll use one of the controls. In this case, for this car, I chose this car because differential drive car, because it's kind of easy to do this. Here we have two inputs, V and omega, and all V is doing is, it's not helping the heading, it's just going straight, right? The angular speed omega is actually controlling the heading. So in this case, I just need to control the angular speed, omega, so it's going towards heading. The simplest way to do it is omega equals k times theta desired minus theta. Let me just get the sign on that right. The sign is right, it is. Yeah, that's right sign. So if you can find a theta desired, then all you need to do is turn the speed. So what is theta desired? Well, we know that this, let's say that the location of this one is known, xg, yg. We know the location of the robot, x comma y. So the theta desired is simply the tan inverse of y minus yg divided by x minus xg. Okay, this will ensure that you get the right heading, and then by controlling omega, you can get it to. So we really don't, we can set v to some nominal speed. Okay, it doesn't really, v doesn't really matter. If you set it to a slow speed, then it's going to go slow, but if you hit it fast, then go fast. This k is a tuning parameter. you need to tune this k, and then theta you usually know. We know the angle at which the robot is going at this very moment. So at this moment, the robot is, this is the heading, this is theta. So we need to know, have some sense of where the robot is, x comma y. We need to know where it is heading towards, theta. And then once we know that and we know the goal, x, g, y, g, we can actually get it to go towards the goal. Okay, so let's take this and see what we can do. So here is some code. Okay, what I'm doing is I've set the obstacles to be off, so there's no obstacles. The position, well, let me just run this, it'll become obvious what's going on. Okay, so the black dot is the goal, and the robot is going straight to the goal. It actually did start at, I think I chose it to start. I did start it at, so this is x, y, theta. So initially it was theta equals 0, 0 being it's heading towards the x-axis, but it actually rotated itself. Uh, so what makes this possible? Well, the same. I'll just show you what I did here. I just computed theta desired, which is the tan inverse. And once I got a theta desired, I used omega is k times theta desired minus theta. Okay, as simple as that. Now let's introduce an obstacle and see how we can change this. Now we have the robot going towards the goal, but there's an obstacle on the way. And then this is a obstacle. And then let's say that the obstacle is right in front. And the robot, well, the goal is here. And clearly the robot wants to go straight. But if it goes straight, it will hit the obstacle. So let's say that we know the xo, yo, and then the radius of this is ro. Okay, so what we do here is that if we think that we're going and hit the obstacle, we want to start turning away from the obstacle. So one way we can do it is we go towards the goal, but the moment we see that we are going to bump into the obstacle, that could be maybe there's a distance sensor, maybe an infrared sensor which tells you the distance. So maybe we could say that we're going to do that a little bit ahead. We don't want to go and start turning the moment we hit the obstacle, right? So what we'll do is we'll create a buffer. Say this is a buffer, or buffer. So the moment we're in this buffer zone, we want to start deciding turning. And the simplest way to do it is to just say, I'm going to just turn at 90 degrees, okay, to this line. Just turn 90 degrees. So if I turn 90 degrees, then I'm just going to go away from the obstacle. And there's some assumption about the obstacle. It's basically a convex obstacle. Convex means the shape is like it's shown there. Concave would be like this. So if it was concave, it was something like this. That would be trouble, right? It would be difficult for it to, but we assume it to be convex. In fact, we'll only stick with circles. So we know that doing a 90 degrees turn, either left side or right side will work. So you could just randomly choose left or right. If you do that, you're good. So how do you do that? Well, we'll just say that if robot is near obstacle, this is something we need to figure out how to do that. Then what we do is we change the theta desired to be tan inverse y. So again, this position is x comma y. So y minus y obstacle, x minus x obstacle. So I found the heading between the robot and the obstacle, the center of the obstacle. And then I would just add a pi divided by 2, which is basically the green direction as shown. So this will get the robot to sort of fly off the tangent. Yeah, so how is this condition enforced? Well, what we can do is we can see we can figure out the distance. So x minus x0 square plus y minus y0 square. So you know that this is the distance from this point to the center of the robot, square root, minus our buffer is less than 0. Okay, what this means is that this condition is less than 0 means that the robot is in this region, the yellow region. So clearly, if it's in the yellow region, then you need to turn. So we switch. We normally going towards the goal, but the moment we are in the yellow region, we just take the robot 90 degrees in the left or right. Okay, so that's pretty much it, what we need for the robot to avoid the obstacle and go towards the goal. So it'll keep going away from the obstacle, and the moment it is away and it is outside the yellow region, it'll try to come back again, but maybe it'll hit the yellow region again go out, and you'll see it'll eventually work. Okay, so what I did was this code. I set it up so that I can just put a flag, and the flag, if I turn it on, if I turn the flag on, then the obstacle will be introduced, and then that logic will change. So here is 1, and I'll show you what that code does. So put 1 and run this. Okay, so the red is the obstacle. Now it's going to obstacle, nothing happens. Now there's a buffer, so it turns away and then keeps going to the obstacle. Sorry, to the goal. The only change I made here is the following. I went into the code. I figured out the buffer. So this is the code which comes into effect. Now I assume this is for n obstacles, but I'm just doing it for one obstacle. I just set it up to one obstacle, but you could have n obstacles defined, and it'll work for n obstacles. I basically find x, y of the obstacle. I find the radius, including the buffer, and then I find the distance. The same thing I told, the distance between the robot and the obstacle, and I also use the buffer here. If that is less than 0, then I just change my theta heading. I take the tan inverse of the heading between the robot and the obstacle, and then just turn it 90 degrees. This direction is a random variable, which I use actually random to seed it. So it'll be, sometimes it'll be 1, sometimes it'll be -1, sometimes it'll turn left, sometimes it'll turn right. And then I just do k minus this. So what happens is, normally I do this theta desired, which is towards the goal. But the moment it sees the obstacle, it changes theta desired. So it sort of switches between the two depending on that. So it gives a priority over moving away from the obstacle. And then you just go till it stops. So this random direction here is -1 to 1. If you set it to, I think, 1, it'll actually go the other way. I'm almost done. So let's. Okay, that was the left one, so I need to put -1, my bad. Okay, I'll run this and then I'll stop. So just put -1. Okay, let me kill this, Control C. Let's put -1, run this. Okay, now it should turn right. Okay, oh, so that's just randomly chosen. There's no good solution. I mean, unless you know something about, sometimes +1 is better, -1 is better, depending on the obstacles, but you will not know that in advance. Okay.